Hello and welcome to another video for programming your TI84 calculator. Here we're looking at a quadratic line regression as you prepare for specifically the SAT exam. As a good example for a quadratic shape of data for best sublime fit, the data in the table shows the temperature on a porch during several hours of the day. Tell whether the data is best modeled by a linear or quadratic model. Well, if you think about your experience, if you live, I think it's called in the olive tree line in our latitudes, such as New York or the Northeast, or those latitudes anywhere around the world. When the sun goes up, when the sun rises, it's cold during the day often. But then as the sun rises up and the day continues, it gets hotter and hotter. And then afternoon, as the sun begins to set, the temperature cools off again. So here you can see that the sun rises at 6 a.m. Temperature on this porch is 45 degrees. By midday, it reaches 68, 70 degrees. And then as the sun sets and goes into nightfall, temperature goes back to 56 and 49 degrees. So this is a good model because it's not linear. It's going up, has a peak, and then comes back down like a quadratic function. So let's see what happens when we take this data and enter it into the Texas Instruments calculator as a good model for quadratic regression. All right, so what we'll do now is we'll go to the TI84 Smart View, CE for the TI84 Plus family, and we'll graph this example of the porch temperature over the course of a day, of a 24-hour day. And the quadratic best sublime fit will be this graph shown here. Notice that I have a good window size setting again for these times from 6 a.m. to, I guess, 9 p.m. That'd be the 21st hour of a 24-hour day. So it spans across, fits the window nicely, and a top temperature of about 80, which you can see in the window settings here if I click refresh. Oh, the top of this is 75. What we'll do is we'll enter the data points first, and then after entering the data points, we'll continue with this graphic. So if you hit stat, you'll come to this window, hit enter, and you should see this table of data points here. In the left column are the hours that the measurement was done. So at 6 a.m., the porch was 45 degrees. At 7 a.m., it was 50 degrees. At 11 a.m., it was 52 degrees. At 1 p.m., it was 68 degrees. So here I used Army time for the prime meridian for afternoon. So 4 p.m. is 4 hours after 12, so that's 16. And 7 p.m. is 7 hours after 12 noon. And 9 p.m. is 9 hours after 12 noon. So we get these temperatures going up and ascending and then going back down to 49 degrees. Please pause the video if you need to enter these data points for these 7 measurements of temperature on the porch. Okay, the next thing we can do is we can hit graph, and we don't have the line yet, but the data points should come up like this in a set. And if your point setting for plot aren't set, you can do second y equals, and then it'll come up to stat plot. Then hit enter or the number 1, and here make sure it's blinking on. You can toggle it on and off. And here we'll use a set of points, and I'll use a box mark, but just to change it so you can see it, I'll choose navy blue. How about that set for this porch? And then when we go back to the graph, the same data points are now in that dark blue for those 7 measurements. Looks like there are 2 kind of outliers. Maybe, however, the sun was shining down on the porch, but clouds rolled overhead, so it measured it as cooler. And maybe these are accurate. Maybe there were no clouds in the sky where these temperatures were higher during midday. But I would say maybe this lower temperature had to do with cloud, maybe cloud coverage for the third one. Next thing we'll do is we'll graph the line of best fit that is a quadratic shaped line. So in order to do that, click stat and right arrow, and then we'll go down to 5 in the menu of the different curve fits that we can do. This is one of the fits to data that we should see. Boom. And y1 is the temperature during the day. Y2 is the measured temperature. And if you click bars, right arrow, enter for y1, y1 will store the equation, and hit calculate, and it will calculate it for you. So here's the screen for quadratic regression. We have that y equals ax squared plus bx plus c, that's standard form, would have an a coefficient of negative 0.316, a b coefficient of 8.992, and a c coefficient of 1.010. And R is kind of low, though. It is still acceptable. It's at 0.72, but we might want to look at the data because I think of that third point. Unless the scientists can say, yes, it was cloudy, and maybe reject that data point, or redo the temperatures, noting the weather conditions if it was cloudy or rainy during the day. Right, usually we want an R that's stronger than 0.729. All right, so if we go to the graph, you can see the line, and I traced it over. You notice how it's being traced twice. That's because I let the computer code it with y equals, but it codes it to 12 decimal places. So then I scribe it down, and then I rewrite it as the red line, rounded to the nearest thousandth. So again, this won't matter much for this local picture of these values. All the values are between, say, 0 and 25, right? 0 and 24. But you can see that it even starts to deviate over here. You start to see the shadow of the blue line if you round to 3 decimal places for this porch problem. But there you have it. There's a quadratic regression for something that's logically a quadratic shaped data that we're expecting. We're expecting it to get warmer from the morning, cold, cold, get warmer, go up, 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 and then turn around and come back down as the sun sets. Right, so I hope this video was useful to you in modeling quadratic regressions as you learn more math and get ready for your SAT exam. Thank you for watching my video.